Imagine going from spinning up your very first GPU VM to architecting enterprise grade multi cloud AI systems in a single year. That's the promise of this course. Learn the building blocks of AI infrastructure, Linux and cloud fundamentals, containerization with Docker and Kubernetes, and secure, scalable data pipelines for AI training, storage, and real world deployments. Master multi GPU and distributed training using CUDA, PyTorch, TensorFlow, and Horovod. Optimize performance, reduce costs, and maximize throughput for efficient scaling of advanced AI workloads. Develop professional grade MLOps skills, track experiments with MLflow, manage registries, automate pipelines with Kubeflow, and deploy production ready models with Fast API, TorchServe, or NVIDIA Triton for real users. Go beyond basics with observability using Prometheus and Grafana, robust security and compliance, edge AI with Jetson devices, and generative AI infrastructure for LLMs, RAG pipelines, and large scale optimization. Every week includes practical labs, case studies from OpenAI, Google, and Tesla, plus a final capstone project where you design, deploy, and showcase your own complete AI infrastructure system. If you're serious about becoming the person who can design, deploy, and scale AI systems, this is your roadmap. Seats fill fast. Join the complete guide to AI infrastructure, zero to hero today, and start building the infrastructure behind tomorrow's AI. Enroll now. Welcome to day one of our exploration into the fundamental systems that power artificial intelligence. As impressive as AI models appear on the surface, whether it's ChatGPT generating language or a vision system interpreting medical scans, none of these breakthroughs would be possible without the underlying infrastructure. AI infrastructure is the true engine behind the curtain, quietly enabling every step from data collection to training, from deployment to inference. Without it, the towering architectures of deep learning would collapse. Our goal today is to peel back the layers, to understand the specialized hardware, the orchestration software, and the operational practices that make modern AI not just possible, but scalable, reliable, and transformative. As we move through this journey, you'll see that AI infrastructure is not just an IT concern, it's the strategic backbone for innovation in the 21st century. At its core, AI infrastructure can be thought of as a three layered ecosystem. At the bottom is the hardware layer, specialized chips, memory hierarchies, and ultra fast networking links. These components determine the raw horsepower available to train and run models. Above that lies the software layer, the frameworks, libraries, and platforms that translate mathematical theory into working models. This includes TensorFlow, PyTorch, CUDA libraries, and distributed training toolkits. Finally, at the top, we have the operational layer, the systems that orchestrate, monitor, and secure large scale AI pipelines. Think of it as a living organism. The hardware is the muscle and bones, the software is the nervous system, and the operational layer is the circulatory and immune system. Together, they form a complete body, an ecosystem that allows intelligence to emerge and thrive. Traditional IT infrastructure was never designed to meet the colossal demands of AI. The difference is not incremental, but exponential. Training a single frontier model like GPT-4 can consume millions of GPU hours and tens of millions of dollars in compute costs. General purpose CPUs, built for sequential processing, crumble under such workloads. Instead, GPUs with thousands of parallel cores accelerate matrix multiplications by factors of 100 to 1000 times, making deep neural networks feasible. But it's not just compute. The data scale itself is staggering. GPT-4 was trained on trillions of tokens, harvested from hundreds of terabytes of text. Feeding this ocean of data into compute requires highly specialized pipelines and storage. And when models finally reach deployment, they must serve millions of users with millisecond latency. These are workloads no traditional enterprise system could ever handle. Specialized AI infrastructure is the only reason we can dream at this scale. To grasp AI infrastructure in practice, we must examine its five critical components. First, compute, the heart of the system, powered by accelerators like GPUs, TPUs, and NPUs, which crunch tensor operations orders of magnitude faster than CPUs. Second, storage, high throughput systems such as distributed object stores, feature stores, and vector databases that keep massive datasets flowing. Third, networking, ultra fast interconnects, sometimes 400 gigabits per second or more, allowing thousands of accelerators to communicate in near real time during distributed training. Fourth, orchestration, tools like Kubernetes and MLOps platforms that automate scaling, deployment, and lifecycle management. And fifth, monitoring and security, the guardrails that provide visibility into performance, detect drift, and defend against adversarial attacks. These five components form the skeleton and nervous system of AI infrastructure, and their design choices determine whether an AI system thrives or falters. Abstract concepts become clearer when we see them applied. Consider autonomous vehicles. They must process camera, LiDAR, and radar data in real time on the edge, but also synchronize with the cloud for fleet learning and map updates. This hybrid architecture, edge plus cloud, is infrastructure in action. Or take generative AI. ChatGPT serves over 100 million weekly users by orchestrating clusters of specialized accelerators with finely tuned inference software. In healthcare, AI infrastructure is tasked with processing 3D imaging data on secure, hyper compliant systems, ensuring both accuracy and privacy. And in financial services, real time fraud detection engines analyze thousands of transactions per second with sub 10 millisecond latency requirements. These examples remind us every flashy AI application you see rests on an invisible foundation of carefully engineered infrastructure. The future of AI infrastructure will be defined by four major trends. First, specialized AI chips. Purpose built silicon for specific workloads will deliver 5 to 10 times efficiency gains compared to today's general purpose GPUs. Second, hybrid deployments. Seamless integration between edge, on premises, and cloud resources will unlock new classes of applications, from autonomous robotics to hyper personalized healthcare. Third, green AI. Carbon aware scheduling, liquid cooling, and efficiency optimized algorithms will become mandatory as the environmental footprint of AI draws regulatory and public scrutiny. And fourth, infrastructure as code. Declarative specifications will allow engineers to spin up entire AI stacks with perfect reproducibility, automating what today requires weeks of manual work. The key takeaway is this: AI infrastructure expertise will not just be a technical advantage, it will be a critical differentiator for organizations over the next decade. Those who master it will drive the future of innovation. When we talk about artificial intelligence, it's easy to get caught up in models, data, and algorithms. But beneath it all, the true engine of AI progress is compute power. The chips we use, CPUs, GPUs, and TPUs, define the limits of what's possible, dictating how fast we can train, how efficiently we can deploy, and how far we can scale. This session is a comprehensive exploration of compute architectures for AI, comparing CPUs, GPUs, and TPUs in detail. Our goal is to help you make informed decisions about infrastructure, to understand not just what each processor does, but when and why to use it. As you'll see, the choice of hardware isn't trivial. It is strategic, impacting performance, cost, scalability, and even the feasibility of your entire AI system. AI workloads are fundamentally different from traditional computing. They demand specialized architectures that go far beyond what conventional CPUs can provide. The hardware you select impacts three critical dimensions. First, performance and training speed. Choosing the right architecture can shrink training time from weeks to mere days, sometimes even hours. Second, cost efficiency. Hardware choice can mean a 10 to 100 times difference in the price performance ratio, the difference between a feasible project and one that breaks the budget. Third, scalability. As model sizes grow into the billions and trillions of parameters, and as datasets balloon into terabytes and petabytes, different architectures scale very differently. Understanding these trade offs is no longer optional, it is the foundation of intelligent AI infrastructure design. Central processing units, or CPUs, remain the workhorses of general purpose computing. Designed for sequential processing with high clock speeds and sophisticated control logic, they excel at orchestration, pre processing, and small scale inference. They are ideal for data pre processing tasks, ETL pipelines, and ML workflow management. CPUs are also excellent for low latency API serving of simple models and lightweight inference. Their strength lies in versatility and unmatched software compatibility. However, CPUs struggle with the parallel matrix operations that dominate deep learning training. The cores are too few, too complex, and not optimized for the massively parallel workloads of modern AI. In infrastructure terms, CPUs are the coordinators, not the muscle. They manage, orchestrate, and prepare, but they do not carry the heavy burden of training large neural networks. GPUs, or graphics processing units, are the true engines of deep learning. Originally built for rendering graphics, their architecture of thousands of simpler cores turned out to be perfect for the parallel matrix math required in AI. They accelerate tensor operations dramatically, cutting training times from months to days. High memory bandwidth ensures that massive datasets flow efficiently, keeping cores fully utilized. Today, GPUs are the industry standard for training and inference across computer vision, natural language processing, and generative AI. Flagship examples include NVIDIA's H100, powering frontier large language model training, the A100, still the workhorse for production systems, and AMD's MI300X, an emerging competitor with high memory capacity. GPUs dominate because they are versatile, broadly supported, and battle tested, yet they remain expensive, power hungry, and in high demand. A reminder that power always comes with cost. Tensor processing units, or TPUs, mark the next step, purpose built AI chips. Designed by Google specifically for deep learning, TPUs are application specific integrated circuits, hardware optimized solely for tensor operations. Their matrix multiplication units, or MXUs, are built for the workloads that define AI training. They offer 2 to 3 times better price performance than GPUs for certain tasks, especially when using TensorFlow or JAX. TPUs also feature high bandwidth memory and scalable pod architectures, allowing thousands of units to work together on massive models. But TPUs are not general purpose. They are specialized cloud only and tightly bound to Google's ecosystem. For workloads aligned with TensorFlow and JAX, they offer unmatched efficiency. For broader ecosystems, GPUs often remain the safer, more flexible choice. TPUs represent the specialization trend in AI hardware, showing what's possible when silicon is tuned exactly to AI's needs. Ultimately, the question is, how do you choose? The answer depends on your workload. For large scale TensorFlow training, TPUs may be the best option, offering unmatched efficiency. For most training and inference workloads, GPUs remain the industry standard, providing versatility, ecosystem support, and performance. CPUs, meanwhile, are indispensable for orchestration, pre processing, and lightweight inference. But the truth is, few real world systems rely on just one type of processor. Hybrid architectures dominate production AI. CPUs prepare and orchestrate data. GPUs or TPUs perform the heavy training. CPUs return to manage deployment and inference APIs. And when evaluating hardware, it is critical to factor in total cost, not just the sticker price, but also power consumption, cooling requirements, engineering time, and operational complexity. The optimal solution is rarely a single chip type, it is a strategic blend, a carefully designed mix that matches compute to task maximizing performance, efficiency, and scalability for your specific AI workflow.